SwayamPrabha. Digital India. Educated India.
So, now that we have established this interfacial heat and mass transfer, we know how the interface actually behaves. Now, let us look at some of the specialty problems right now. Okay? And one of the specialty problem is basically droplet evaporation and combustion. Okay? Why is it important? As I said that droplet evaporation is fundamental to almost all applications that you can think of. Okay? From gas turbines to spray dryers to surface patterning, whatever you can think of. This droplet may be in the sessile mode. Sessile mode means it may be on a surface like this, or it can be in a spray mode where the droplet is basically injected as a part of a spray, okay, like this. There are many droplets. Okay. So, these droplets basically represent a multiphase system, right, because there is a liquid core and then there is a gas exterior, right, whatever it may be. It need not be water, it can be anything, okay. And the liquid core can be multi-component, multi-species kind of a system as well, right. For example, as I said, water ethanol was one example, okay. These days, for example, when we go to renewable type of energy, okay, people use something called biofuels, say for example. So, biofuel is a mixture of n number of hydrocarbons, okay, from very small hydrocarbons to very large hydrocarbons, right. So, this liquid phase usually have a multi-component nature or a multi-species nature to it, right. Apart from that, so that is the gas phase, okay. This is the sessile droplet. Sessile droplet, for example, is used in surface patterning a lot, right. So, these sessile droplets might contain, you know, polymers or nanoparticles, okay, and it can be used to create structures on the surface, right. Similar things can be done in biological applications also, okay, like flow cytometry and things like that will all have this droplet based framework, okay, and they will have this droplet based thing is also used in microfluidics application, for example, where a droplet containing cells, okay, may be actually used for some point of care type of diagnostics, right. Okay. So, there are many applications of droplet vaporization, okay, and droplet deformation, droplet atomization, and it covers regions from healthcare all the way up to combustion, that means all the way up to power generation. So, it affects every part of our life, so to say. Okay. However, the combustion part is a little bit more special. It deals with only combustion, that when these droplets actually participate in combustion, what happens. Okay. So, in this particular series of lectures that will follow, we will first try to anchor what is droplet vaporization, how we can actually analyze droplet vaporization, and then we will go on to a little bit more special topic concerning combustion. Okay. And we are going to use a PPT as well as the journal to actually look into what we can have. Okay. Now, what is the phenomenology of droplet evaporation, right? That is the key thing. Okay. Let us consider one droplet now, that is because multiple droplets had got its own problems. Okay. There are interference between multiple droplets. Okay. So, this is important, droplet vaporization, because most of the technological processes that we talked about just now, it is desirable basically that you want to gasify the droplet or even combust the particular liquid in a gaseous medium, okay, at a fast rate or at a controlled rate with various degrees of control, right. We want to do that, right. We basically want to control this evaporation rate, okay, in order to achieve certain goals, whatever those goals may be, right. So, what does this droplet actually do? If you carefully look at the droplet, okay, this is a isolated droplet that we have put over here. This is isolated. That means, let us not assume that it is surrounded by any other droplets. It is like one building block that we have taken out. Okay. So, there is what this droplet actually do is that there will be heat and mass exchange between the droplet as well as the gaseous medium in which it is in, right. Okay. It is important. So, what will happen is that there will be heat that will come from the ambient, and the droplet will generate the vapor which will actually get mixed with the ambient, right, that is vaporization. The reverse you can talk about is condensation, right. So, there will be heat that will be given out by the droplet, the vapor that is there around the droplet will just condense. Okay. So, in that case the droplet size will increase. So, this single droplet actually exchanges heat, mass and momentum with a gaseous medium, right. So, if I want to analyze this droplet, right, okay, in its complete and holistic view, okay, what are the things that we need to do, right, that is a pertinent question over here. Forget about it is combusting or not, just to do the heat and mass transfer, what equations do we need to write, what is the mode of analysis that we need to do, right. Okay. So, the complete analysis will involve basically 4, emphasize the word 4 interacting processes. One is a liquid phase transport, that means what happens in the liquid phase, that means within the droplet what happens. The gas phase transport, that means what happens in the gas phase, okay. The phase change at the liquid and gas interface, right, and if you have combustion then what are the chemical reactions that are taking place in the gas phase, right. These are the 4 things that we need to answer, right. So, we have to basically solve the governing equations, that is mass, momentum, energy, species, right, in both the phases, that means in the liquid phase, in the gas phase. These are all the equations that we derived, right, so far in the lectures, right, how to write equations in the liquid phase and in the gas phase, right. So, here in this case this is a very dispersed kind of a system, it has got a well defined boundary, it is not a problematic boundary anymore, not in this spherical configuration, because the droplets we are assuming it is spherical, okay. But you need to solve for the liquid phase, the gas phase, the phase change as well as the chemical reactions. These 4 things needs to be solved properly, right. What are the important considerations for this? Okay. Important consideration is that there could be relative motion between the droplet and the gas phase. This is normally it is true, because for example, we are spraying droplets, okay, into a heated environment, right. Let us take that example, right. Okay, they are spraying something in an environment. Okay. So, the liquid phase velocity or the speed with which the droplets are injected into that particular phase may be different from whatever is the gas phase velocity, right. Okay. So, the gas may be moving at a different, so it is, say you have a pipe, there is a flow which is going at a velocity V1, right, you are injecting droplets into this flow field, right, at a velocity say for example V2. Right. So, this V1 may not be equal to V2, in most of the cases they will not be, right. So, there will be a relative motion between the gas and the liquid phase. Okay. There will be something called a Stefan flow due to surface gasification. As this droplet evaporates, right, the interface is actually shrinking, okay, or expanding depending on which way you think it is, right, either it is a evaporation or it is a condensation phenomena. So, there is something called a Stefan flow which is created due to this surface gasification, that means there is conversion, okay, of species from one phase to the other, that is what is happening, correct. Now, there is also droplet drag. If there is relative motion between the droplet and the gas phase, there has to be drag, right, because if say for example, you put a cylinder in a flow field, right, you develop a drag on the cylinder, right, that is very common, okay. But that drag comes because of the relative motion, pressure drag, and there is viscous drag also. Same drags will be applicable over here also, not in that exact form, but it will be applicable, right. Similarly, there will be internal recirculation also inside the droplet. When there is a flow outside, why should not there be a flow inside, right. The droplet is also in the liquid phase, right. So, there will be a flow inside. So, all these important considerations needs to be taken into account if we want to solve this full problem, right. Okay. So, given that introduction, let us look at some of the interesting features, okay, of this now, okay, and some of the data that comes from our group, was essentially from my group. So, I can share a few data with you, okay. Like for example, as I said, we have assumed that the droplets are normally very spherical. That is true in some of the cases, right. In some of the cases it is not, okay. So, you get this catastrophic shapes, right, got it. So, this you cannot tell that it is spherical, this is non-spherical, right. So, this becomes a problem in which the interface is not very well defined, right. So, there are situations like hydrodynamic, thermal and shear instabilities, okay, that leads to configurations like this, right. but we will come to that later. Okay. So, there may be also temperature and concentration species profile within the droplet because of internal recirculation, right. So, as you can see in this particular configuration, okay, the species profile is not very symmetric, right, it is shows that kind of a behavior, is not that so. That happens because there is a flow that is generated inside the droplet. Okay. Forget about this for the time being, this is if you have particle matter within the droplet, how do they accumulate. Okay. One other interesting thing, so these are some of the examples where you can see that why the droplet is very useful. Okay. Now, one other interesting thing that will come after this one, that most of the time people assume that there is something called a spherically symmetric model, right. What is a spherically symmetric model? Spherically symmetric model is that a model of a droplet which is actually vaporizing into a quiescent ambient where there is no flow. Okay. So, the droplet is nice and easy sitting over there, there is no flow. So, if you are considering flow around the droplet, there are no such flow, right, and it is isotropically actually vaporizing inside a quiescent environment. This particular thing is very hard to achieve because normally even your room, okay, at this condition actually has a flow. Okay, if you put an anemometer or a pitot tube over here, you will detect a flow, and that flow is not very trivial. Okay. So, by spherically symmetric model we mean that the droplet is vaporizing in a spherically symmetric fashion where there are no flow effects. When there is flow, the symmetry is usually destroyed, as we will show in the next one. If there is something like a buoyancy or if there is something like an external flow, you can see what happens within the droplet. This is basically the outer flow streamlines, okay, streamlines of the outer flow. You can see that there is a flow separation that happens at the back of the droplet. This is very common. If you guys have done fluid mechanics, you know that behind a cylindrical or a spherical obstacle there is always a flow separation. The similar thing happens within the droplet also. In addition, however, you can see that there are recirculating flows that are created within the droplet, right. Okay. Similarly, okay, so you can have another situation in which the flow is very high, probably like a little bit of a high velocity flow, and you have basically two recirculation zones, right. So, we are not considering these two at all in a spherically symmetric analysis, right, because there is strong flow inside the droplet, whatever the nature of that flow may be. Okay. It can be buoyancy driven flow, it can be imposed flow. So, it can be natural internal recirculation, it can be imposed recirculation due to the gas phase velocity, got it. Okay. So, that part is very important. Okay. We will look at this a little bit later. Now, if we want to solve this equation along with combustion, okay, and this is not to basically scare people away. Okay. So, basically this is the droplet, this is where the combustion front is, basically what we call the flame, and this is basically the gas phase flow field, right. Okay. Now, you can see it is a multi-component molecular diffusion. When you have combustion, you have complicated kinetics, the chemical kinetics is extremely complicated. So, you can have as much as 50 species, okay, 250 reactions, sometimes even more. Okay. There will be non-luminous thermal radiation, there will be UV emission. So, you have to solve for all those things. Okay. So, you have a mass conservation, you have multiple species conservation equation that you need to solve, and you need to solve it for both phases, that is the interesting part, right. Okay. Then you have the energy conservation equation, and from the droplet surface you have to take into account the surface regression, the evaporation, condensation, radiative heat addition. In the droplet interior you have to solve all these equations, right. So, it becomes a framework and all these equations will be coupled with each other based on the interface conditions. They will be all matched at the interface, the solutions have to match at the interface, right, and they have to physically make sense also, right. So, this is a very onerous job, as you can understand, right. There are a lot of reactions floating around, there are a lot of things that you need to solve, there is gas phase, there is liquid phase and all these things. Okay. So, but fortunately the spherically symmetric assumption offers a very good tool, right. It offers a solution without much of a headache, right. So, before we go there and we will emphasize on something called a d square law, and then we will try to prove that how it actually comes. Now, some people, some researchers actually did some experiments, right, using this kind of a in using this kind of a droplet. And they what they did was that they suspended a droplet, okay, they maintained it probably in a box or something where there is no flow. So, no flow, got it, okay, and it is quiescent. So, the spherically symmetric assumption can be applied. When they did the measurement and when they normalized the droplet diameter by the initial droplet diameter square, right, and here you are plotting something like delta t by d naught square, right. Forget about the time scale, that is not important as of now. Okay. So, the important part is that d by d naught square. Okay. So, when they divided the instantaneous droplet diameter with the initial diameter of the droplet, so what they basically did was that perhaps they took a camera, okay, and they basically monitored how this droplet is actually evaporating. So, they were basically calculating the droplet diameter at each time instant, okay, and after they were done with that, okay, they squared the diameter and they divided it by the initial diameter square, right, and they plotted it. What they saw was something, so it will be always 1 to 0, right, because the droplet will always shrink, and this is a evaporation case, let us not consider condensation, okay, and they saw that they got a straight line, a linear line, right. They got a linear, no matter what fuel they did with, okay, they always got a linear profile. So, this linearity of the profile suggests basically that with time, okay, there is a constant slope. So, this means that d by d naught square, okay, will be basically some kind of a constant slope, some kind of a constant slope kt, right, no matter what happens with how you normalize time. So, it shows that there is a constant slope always. The slope value can vary depending on what droplet you are dealing with, but they got a constant slope, right, no matter which droplet they actually dealt with. Okay. So, this was actually proposed in the famous d square law, okay, d square law by Law and Scirinniano. Okay. So, they actually proposed that there will be something like a d square law which the droplet has to obey, okay, in the case of this quiescent spherically symmetric evaporation. Okay. Now, what is the prelude to that d square law? Okay. So, first and foremost, it is spherically symmetric. Okay. Forced and natural convections are neglected, not just neglected, they are assumed to be negligible, right. So, this reduction leads to a one dimensional analysis, okay, because there is no flow, there is no spray effect. That means, there is one droplet is isolated and it is all by itself in an infinite environment, there is no other droplet that is present. So, it is very restrictive, right. Diffusion is the rate controlling parameter, that means the liquid does not move relative to the droplet center, that means there is no internal motion of the liquid, got it. The surface regresses into the liquid as evaporation happens, that means the surface slowly shrinks, right, that is common, right, a droplet should shrink. Okay. Therefore, heat and mass transfer in the liquid occurs only because of diffusion with a moving boundary, but not convection, got it. So, there are no convection effect, it is basically a diffusion problem, there is no flow inside the droplet, outside the droplet, okay. There is heat and mass transfer only due to diffusion with a moving boundary. So, it is a slowly shrinking droplet, okay, where there is no flow, okay, and it is an isobaric process, it is a constant pressure process. So, we are not varying the pressure, constant gas phase properties, okay. That is because the gas phase properties, if for example, due to evaporation or during the time of evaporation, during temperature changes, if the specific heat, thermal conductivity, diffusion coefficients, density, etc. varies, you will have a different problem. So, you are assuming that is a constant property. Now, the sixth assumption is the most important one. It says gas phase quasi steadiness. What is quasi steady? Steady means steady, that means there is no temporal derivative. If you take a temporal derivative, it will come out to be 0. Quasi steadiness actually means it is steady with respect to certain time scales, right. So, because there is a significant disparity between the liquid and the gas, usually that is the case, it is of the order of 1000, right. Liquid properties at the droplet surface, okay, at the droplet surface changes at a rate much slower than the gas phase transport processes, okay. This assumption actually breaks down far away from the droplet surface, we will see when it breaks down, but the liquid properties at the droplet surface, that is the regression rate, shrinking of the droplet, the temperature and the species concentration, if there is a multi-component thing, changes at a rate which is much lower than the gas phase transport processes. So, that means the gas phase changes so fast, right, that the liquid is almost seeing a steady gas phase outside. It is not able to detect what is going on in the gas phase, because its own movement is very slow, right. So, that is one of the key important parameter, that the gas phase with respect to the droplet is actually a quasi steady thing. Okay. This will happen if there is a very fast process that is going on, and if you are very slow, then you would almost see like a steady thing. This happens everywhere, like for example, with your human eye, right, with a human eye. In some cases, if I change something very quickly, okay, you may not be able to see that the difference, the subtle difference. So, why that happens? Because I am actually not able to respond that fast, right. So, if my response time is slow and the gas phase response time is very fast, then of course, you will see the gas phase almost like a quasi steady kind of a situation. Okay. Now, the gas phase quasi steady, let us look at some of the characteristic time scale analysis, right. Now, in a standard environment where there is a gas phase heat and mass diffusivities, like for example, so the gas phase heat diffusivity is alpha g, mass diffusivity is say delta g, okay. They are usually of the same order, right. They are usually of the same order, which is roughly given as 10 to the power of 0 centimeter square second inverse, right. Okay. A typical example is a Lewis number equal to 1 kind of a situation, right. Okay. Now, the droplet regression rate is of the order of this 10 to the power of minus 3 centimeter square plus second inverse. Okay. That the droplet from the experimental data, if you consider that how it vaporizes, this is the rate of regression, surface regression, right, how the droplet diameter is shrinking, right. That happens in the order of 10 to the power of minus 3 centimeter inverse second. Okay. This happens actually in a time scale of 10 to the power of 0, right. This is for conventional hydrocarbon fuels evaporating in the atmosphere, right. So, that the ratio of the same order of liquid to gas densities, okay, that is this is liquid, this is gas, okay. If you divide these two things like the mass diffusivity divided by the regression rate, it means essentially that the gas mass and heat diffusion occurs much faster than the droplet regression time, got it. So, the mass diffusion, the mass transfer that is happening from the droplet surface, okay, is happening at a much faster time scale compared to the regression, and these ratios will actually show you, one is 10 to the power of minus 3, one is 10 to the power of minus 10 to the power of 0, right, and alpha and delta are basically the diffusive time scales, right. So, it essentially means that when you have a disparate density difference like this thing, rho liquid by rho g, you can readily see over here, okay, because this is of the order of 1000, there is this is also of the order of 1000, right, which is very clear from over here. This is of the order of 1000, is not that so? Okay. So, it essentially means that the diffusion process is very fast compared to the regression or the surface regression. Okay. So, thus the gas phase processes can be assumed to be steady, okay, time independent, because the surface almost freezes during that period, the surface does not see anything else, okay, with the boundary variations occurring at much longer scales. Now, the question then actually remains that what value of this d, that means the separation distance, right, this assumption actually breaks down. That means when the diffusion time is equal to the surface regression time, right. So, when the surface regression time becomes equal to the gas phase heat and mass diffusion time, that means this particular relationship when it is actually valid, right. So, d naught square by k will be equal to what value of d, okay, what value of the diffusion length, right, for which these two time scales will be the same, remembering that these two is of the order of 1000 always, right. So, once you do that, you will find that this d infinity is actually 32 times the droplet diameter, okay. So, that means if your distance is less than that, okay, you are okay. You can assume this gas phase quasi steadiness, but if you are far away, right, then of course, this will not be valid, got it. So, it is 32 times the droplet diameter. At that particular distance you can actually have this thing breaking down. That means, you cannot apply gas quasi steadiness at that kind of a distance, right, which is 32 diameters away from the droplet, okay, which makes kind of sense, right, because this is basically the scale at which the droplet surface actually regresses. This is the scale at which the vapor will travel to that kind of a distance. This d infinity is basically a distance, right. So, so long the distance is small comparable with the droplet diameter, okay, this assumption is still valid, right. That means, your quasi steadiness is valid. However, if the distance becomes very large, that means, you are trying to compare whether a point which is 32 diameters away from the droplet is actually quasi steady or not, then that particular assumption is not valid. Got it? Okay. So, that is roughly a rough figure 32 diameters. So, that means our model will be valid for less than that, right. So, this d square law is very powerful, but it comes with its own caveats, that these are the assumptions that we have stated, and we have assumed that it is a liquid vapor. Of course, if this difference between the densities of the liquid and the gas, if they are very small, okay, very small, okay, like for example, if you go to supercritical type of cases, okay, so that could be very small, okay. So, in that particular cases you cannot assume actually quasi steadiness, okay. So, be prepared to understand what assumptions and why they are applied and why it is valid. That is an important part of this argument, okay. So, as some of the additional assumptions are that you have to assume a single fuel species or whatever species that you are assuming is a constant and uniform temperature, droplet surface temperature. That means, there is no spatial variation of the droplet surface temperature, there is no temporal variation of the droplet surface temperature as well, okay. And it is basically a gas phase model, we will not do anything to the liquid phase, okay. It is basically a gas phase model. So, as you will find when I do the modeling, it will be just a gas phase model, and we will do something to the liquid phase, but not that much. The saturation vapor pressure exists at the droplet surface, okay. That means, the vaporization happens through the obeying the Clausius-Clapeyron type of equation, okay. So, the evaporation at the surface is always at a thermodynamic equilibrium, okay. So, it produces the vapor which is at a saturation pressure corresponding to the droplet surface temperature, okay. So, it is not that fast a process also, that the evaporation is always in a nice thermodynamic equilibrium state, okay. So, it is not away from equilibrium, okay. And then there is no effect like Soret and Dufour. These effects basically comes due to the second order effects, these are all second order effects, so these are neglected, usually they are, and the radiation effects also are neglected, got it. So, these are the 10 assumptions basically, okay, that goes into the making of the d square law, which is experimentally people have validated, right. But however, I did not do the math as of now. So, the math will be done in the next few slides or the next few journals entries, but I want you to kind of understand before we go to the next lecture, okay, to state that the d square law is valid experimentally, people have seen it, right. And in order to apply it mathematically, there are a set of assumptions that we have said. Two principal assumptions are that there is a gas phase quasi steadiness, that is very important, right. The liquid phase does not feel any flow, does not feel anything essentially, it just vaporizes. The saturation vapor pressure exists, so it is a thermodynamically equilibrium process always, that is how the liquid is going into the vapor phase. There are no second order effects, okay, forget about second order effects, that may be important in some specific applications, not for this, okay. And you have a constant and uniform surface temperature, right. So, whatever heat that you are supplying to the droplet basically goes towards the latent heat, okay. And of course, there is no spatial change in temperature, that is because it is a spherically symmetric case, right. So, there is no temperature gradient also, okay, within the droplet as such, okay. So, when there is no gradient within the droplet, can you imagine what that is called? So, when you are dumping heat to the droplet there is no internal temperature variation within the droplet, not with time, but with space, right. Why is that? That happens because the droplet has got a very high value of thermal conductivity, right. So, when the droplet has got a very high value of thermal conductivity, it is called basically an infinite conductivity approximation. That means, whatever heat that you are supplying is only the during the initial phase, the droplet surface, the droplet core versus the droplet surface does not see any temperature gradient. Okay. So, the heat is instantaneously conducted, right. Now, if this temperature does not vary with time also, then that means that whatever heat now you are supplying to the droplet is basically going towards heating or evaporating the solvent, right. So, these are the few assumptions that will come. This is an important assumption, and once we do the math, we will see that what is the implication of this particular assumption. Take a look. So, remember the constraints, that what are the time scale analyses that we did. Okay. And remember, another important thing is that the diffusion is a rate controlling step. Okay. There is no convection effect at all, and constant properties and other things are fairly obvious. So, we should not be bothered about that. Okay. So, what we do is that we finish this lecture over here. We will then start and derive this d square law from first principles, right, and show that why it should come constant, basically match the experiments. Okay. And there once we write the equations, you will see that we will write only gas phase equations, mostly gas phase equations with some limiting boundary conditions. Okay. So, it will be better if we do it in the next class and complete the droplet spherically symmetric, then we will move to more complicated cases. Okay. Thank you.